I am Ito from Tokyo University of Science, Japan. So I will present about these topics. Limit state design assumes the severe damage on the buildings. So this is a design flow. One of popular limit frame analysis is to utilize the lower boundary theorem. By using this theorem, only the equilibrium is considered. Furthermore, to formulate the linear equation of this method, the sum of square of stress are considered as a norm, and this norm will be minimized. Furthermore, this dissatisfaction matrix D is considered here. This is the description of this minimized problem. To obtain minimum stress field, the norm is minimized. To solve this problem, Lagrange method of indeterminate coefficient is applied. This matrix is called as Schur inverse matrix. Here we focus on the limit analysis of bracing frame structure. To keep the high seismic resistant performance of building frame, the bracing structure is usually adapted. During the seismic design procedure of bracing frame, these design points are considered. Here I will explain the geometric expression for understanding this proposed method. First, the simple braced frame model is considered. The equilibrium condition is written like this. This equation can be drawn as like this with a straight line. So the minimization of sum of square of Q and M is considered. This equation can be expressed with this contour. So this equilibrium is considered. The minimum stress field can be solved at this point. Furthermore, the generalized norms considering dissatisfaction weight like this can be expressed. You can see the equation with this ellipse. So this equation can be drawn as this contour, and the minimized stress field can be solved at this point. So the minimum stress field as design point can be controlled by the generalized norm. For example, you use the larger dissatisfaction weight, or D2, on brace member. The small sharing ratio of brace is obtained. Here, this middle right steel braced frame is analyzed with minimum norm stress analysis. In case of same strength on tension and compression member, the local story failure mode is occurred. Also, the plastic hinge on beam end is formed. When the post-buckling strength is considered on compression member, the strength of each member is assumed like this. And from the limit of state analysis with this condition, this failure mode is occurred. Especially the plastic hinge is formed on the joint of beam and brace. It means that this unlikely failure mode is expected. Anyway, the minimum normal stress analysis is performed here. The uniformly dissatisfaction is considered. First, all D equal 1.0. This is the analytical result. You can see that the moment at the joint of beam and brace is 0. If you will refer this result, the beam end failure mode is expected. Also, you can see the same stress on tension and compression brace member. It means that you must keep the same strength on each brace. Sometimes it is not easy. Next, the generalized norm is composed which any dissatisfaction weight is combined on each member. So this figure shows the analytical result of case B, which is a small dissatisfaction weight on tension brace is considered. You can see that the different axial force on brace member and the small compression stress is equivalent to post-buckling strength. However, you can see that the large moment appears at the joint of beam and brace. So this is the analytical result of case C. To prevent the unlikely failure mode of beam brace joint, the large dissatisfaction weight on this joint is considered. You can see that the moment at the joint of brace and beam becomes small, and the moment of beam end becomes larger than the joint. So, on the previous slide, do you remember this equation? By use of this equation, dissatisfaction weight D can be solved like this. Target stress field versus compatibility on each failure mode. Okay, so this four-story brace frame is calculated by inverse problem to calculate the dissatisfaction weight. So, to perform the inverse problem, the target stress field and failure mode are considered like this, and the dissatisfaction weight can be calculated. So this is the result. So the size of a circle is proportional to the dissatisfaction weight. You can see that the large dissatisfaction weight obtained at the joint of beam and brace. So I conclude this presentation. Thank you for your attention.